This is AP Calculus AB. This is homework 7.2 part 3. I've been asked to do a few of these problems for y'all. I'm going to do 15, 16, and 18. And as an added bonus, I got a new laser. Check out that little fella. Number 15. We can't integrate this directly. That would be preposterous. What we want to do is we want to set u equal to something so that we find its derivative is the other part of the problem. Now, I think you would agree, don't write this down, if we set u equal to tangent of x and we found that derivative, we would get secant squared of x, and that's not gonna be helpful. Things aren't going to cancel. So our only other choice is to see what happens if we set u equal to natural log of the absolute value of secant of x. If we find the derivative with respect to x of both sides, the right side, to find the derivative of natural log of something, you take the derivative of the top, the numerator is the derivative of the argument, and the denominator is the original argument. The derivative of secant is secant of x tangent of x. And then look how convenient this is. The secants cancel. So we were able to accomplish what we wanted to accomplish, which was we set u equal to something and the derivative of that thing is in the problem. It means things are going to cancel wonderfully. If we multiply both sides by dx, and then divide by tangent, we get 1 over tangent of x du is dx. That's beside work. Substituting, going to replace natural log of the absolute value of secant of x with u. Going to replace dx with 1 over tangent of x du. Conveniently, the tangents cancel, and we're left with integrating u with respect to u. Integrating u with respect to u is pretty simple. Add 1 to the exponent, multiply by the reciprocal, add your arbitrary constant. U isn't actually u. U is natural log of secant, absolute value of secant of u. Nice laser, am I right? So this is going to be 1/2, and then it's natural log of the absolute value of secant of x, and that whole thing's being squared, plus your arbitrary constant. You can leave the answer like that, or if you wanted to just make it a little simpler, you could write it like this, which means the same thing. So there's 15. Hopefully that's helpful. It's not an easy problem. I'm not suggesting it is. I'd be surprised. I'd be surprised if they had a problem like this, and if they did, it would be multiple choice. You'd figure it out. Number 16, well, if we take the derivative of secant, we're against secant times tangent, which is not the other part of the problem. So our only real choice here is to see what happens if we set u equal to natural log of the absolute value of secant of x plus tangent of x. The derivative of natural log, once again, you take the derivative of the numerator and you divide it by the denominator. So the derivative of secant is secant tangent, I believe. The derivative of tangent of x, well, that's secant squared of x. And this is all over the original argument. That's how you take the derivative of natural log of something. Now this we need this to be the same thing as this secant of x, and it sure does not look like it is. But there is a GCF in this numerator. Both of these terms have a secant of x. If we factor that out to the front here, yes, I like my laser. We're left with tangent of x plus secant of x. And the denominator is secant of x plus tangent of x. Since we are multiplying on the top, this is all the entire denominator. We can cancel these out. So this actually, conveniently, what we set equal to u, the derivative, was the rest of what we were taking the integral of. So this is going to work. So that makes du equal to secant of x dx. So 1 over secant of x du is equal to dx. That's all my side work. So integrating, we got secant of x. We're going to replace natural log of the absolute value of secant of u plus tangent of u, or secant of x plus tangent of x with u. And dx, I'm going to replace with 1 over secant of x times du. Secants cancel. All we are integrating now, conveniently, is u, with mad props to u. Add 1 to the exponent, multiply by the reciprocal, add your arbitrary constant, resubstitute in for u, and you got this bad boy integrated. How about that, y'all? See, 18 is the last one. This one, they're kind of giving you a head start because they're telling you what to set u equal to. So let's do that. Let's set u equal to 2x minus 3. It's going to make du over dx equal to 2. It's going to make du 2 dx, and it's going to make dx 1/2 du. Let's throw that in right now and see what happens. Please note, this is the cubed root. It is not x cubed. So that's not super clear, and just want to make sure that that is clear. So we got x, and then we have the cubed root of u, replacing dx with 1/2 du. Now at first glance, you're like, well, this problem can't be done because there's still x's in the problem. But fortunately for us, we have a direct relationship between u and x, and it's easy to get x by itself. So I'm going to take this equation here, and I'm going to solve it for x. Whoops. Now you might be wondering, why did I not distribute the 1/2? Because I noticed in my answers they have brought out a coefficient here. So I'm not going to distribute any of my coefficients. So that means that I can take this x value and I can replace it, this one right here, with 1/2 the sum of u plus 3. I'm going to rewrite the cubed root of u as u to the 1/3. Now at this point, I'm going to factor out to the front this 1/2 and 1/2. This is all one term. So this is not a GCF. I'm multiplying a half times a half and getting a fourth, and I'm going to write it in front. That eliminates 3 of my answers, by the way. I'm going to also distribute the u to the 1/3. When you multiply with the same base, you add the exponents. Should be in parentheses. So should all these answers. I apologize. So that leaves us with A is the answer. It's the one that matches. And it's ridiculous that these don't have parentheses. I just assumed that's something I screwed up. So hopefully that helps for 15, 16, and 18. And the key's updated because I was missing the last page. I apologize for that. Peace in the Middle East.